All right. Definition 6. The union of collection of sets is the set that contains those elements that are members of at least one set in the collection. So if we take set A1, union A2, union A3, we write it like this. This denotes the union of all of these sets. The intersection of collection of sets is the set that contain those elements that are members of all the sets. And we write intersection of collection of sets as such. That's A1, A2, all the way through A sub n. We're going to start with number 20. Let A, B, and C be sets. Show that A union B is a subset of A union B union C, and like the tradition, we're going to pick an X in the A union B. Well, what this means, X belongs to A or X belongs to B. In either case, X would belong to A union B union C for sure. Since it is in A or B, well, it's automatically in that set, because a union would be in at least one of them. Part B says A intersect B intersect C is a subset of A and B. Well, let's see, or A intersect B. Suppose, let's assume X belongs to A intersect B intersect C. So on the left side, right? Then X is in all of the three sets, meaning X belongs to A and X belongs to B and X belongs to C. What was I? X belongs to C. So specifically, X belongs to A and X belongs to B. And therefore, X belongs to A intersect. There it is. You could say hence, you could say yield, many different ways you could say that. And the third case, prove that A minus B, the set A minus B minus C, is a subset of A minus C. Well, let's see. Again, we start with, suppose X belongs to A minus B minus C. Then X is in A minus B for sure, but not in C. Since X belongs to A minus B, I should say, we know that X belongs to A. And X does not belong to B. We know that because it's A minus B. since x belongs to A and x does not belong to C because it's minus C, x belongs to A minus C, which is what I want. I was making sure that's what it is. (22) Show that if A and B are sets with A a subset of C, then A union B is B. Okay, well, let's see. Suppose X belongs to A union B. Then X belongs to A or X belongs to B or to both. Oh, actually, X belongs to A not or, and X belongs to B since A is a subset of B. Right? That's, then I should say either. X belongs to A. If X belongs to A, it automatically belongs to B because A is a subset of B. Or X belongs to B. Well, in either case, X belongs to B. Now, we're going to go the other way. Since that's an equal, you have to show forward and backwards. Well, suppose X belongs to B. Then X belongs to A union B, because this indicates that X is in B. It could be in A, but even if it's not, it is in the union. And that pretty much shows that it is in the union. Fairly simple. All right, how about here? Well, the same deal. Suppose X belongs to A intersect B. Then X belongs to A, which means automatically X belongs to B because it's a subset, right? Or it could be that X belongs to A and X belongs to B even before that. Either way, it's in both. So either case, X belongs to both A and B. Now, if you go the other way, let X suppose X belongs to A. Then X belongs to B as well, since A is a subset of B, and hence X belongs to A intersect B. All right. Number 24. Prove the second associative law on table 1 by showing that if A, B, and C are subsets, sets, then A intersect B plus C, so those are two sets, is the same as A intersect B intersect C. Well, all right. Suppose X belongs to A, set A intersected with set B intersect C. Then X must be in A and in B intersect C. Hence, X must be in B and X must be in C by definition. So since X is in both A and B, then X belongs to A intersected B. And X belongs to C, therefore X belongs to A intersected B and C. Now the other way around. Again, it's an equal, you have to go forward and backwards. Suppose, or suppose X belongs to A intersected B, this set intersected with C. Well, what does that mean? Then X must be in A intersected B, and X must be in C. Hence, this indicates that X is in A and X is in B. So that we already know. And we already know it's in C, therefore X belongs to A, X belongs to B intersected with C, and X must be in A intersected with B intersected C, since it's in every one of these sets. And that's the backwards, right? Yeah, there you go. (26) Let A, B, and C be sets. Show that A minus B minus C is the same as A minus C minus B minus C. A minus B minus C. Okay. So suppose let X belongs to A minus B, this set, minus C. Then X belongs to A for sure, but neither B nor C. Then X belongs to A minus C because it's in A, right? But X does not belong to B minus C because it's only in A. So X belongs to A minus C minus B minus C. That's this direction. Now we go backwards. Suppose X belongs to A minus C, this set, minus B minus C. Well, then X belongs to A minus C, and X does not belong to B minus C. Therefore, X belongs to A, and X does not belong to C for sure, and X does not belong to B. Therefore, X belongs to A minus B because of the first two, minus C because it's not in there either. And that's the other direction. Alright, so on this, draw a Venn diagram for each of these combinations of sets A, B, C. I want set A, this is set A. I want set B union C, B union C. So we're calling this A, we're calling this B, and we're calling this C. Now the nice thing about the coloring I'm using, if you overlap, you get the green color. So there's the solution right there. Anything in that will satisfy this. Now I'm going to go for not A, anything but A. Not A. I shouldn't say what A. the complement of A. That's what I meant to say. Complement of A is everything that you see. Now, what's the complement of B? There's the complement of B. Now, if you pay attention, you will notice that complement of B, the overlap is the green, because this is intersection. If it was OR, I would have taken everything that's shaded. But in this case, I'm just looking for overlap, and the overlap is the green. So if you pay attention, up till now, the solution, the green, right? So I'm going to take the yellow out, and I'm going to take this out. So up till now, the solution is outside of those, right? Okay. There, better. Let's keep it like that. There. For now, let's keep it like that. Intersected with, oh boy, intersected with, not C. Not C would be anything other than this. And it looks kind of like blackish color, right? Not the lighter one, the darker one. And the darker one, if you really pay attention, and again, we want those because you're looking for intersection. Now, if we look at this set, B, A minus B. A is the red. I just want to take out B. If I take the set A minus C, A is the red, minus C, A minus C, there, it's that set. And if I take B minus C, this is B minus C. So A minus B, A minus B, yeah. Now, I'm looking for the union. If I was looking for intersection, I'll be looking at the very dark colored one. But the fact that I'm looking for the union, it's anything that's shaded. There. And the last example I have, set A sub I, so A sub 1, for example, is all the way to I, is -2, -1, 0, and 1. A sub 2 is -2, -1, 0, 1, and 2. A sub 3 is all the way down to 3. A sub 4, A sub 5. If I take the union of those, the union of all of these sets, since you go all the way to n, you go all the way to n. If I look at the intersection of those, the very first, only one. So these are common in all. You take the least one. The next one will go up to 3, but the intersection goes up only till 1. And that's pretty much it for this section.